Okay, so we continue with the with continuity for the most part, and so the big topic yesterday was the inverse. Well, the algebra and the inverse of the continuity of the inverse. So we did discuss a little bit of the meaning of the continuity in the first place, but for the most part, it is about continuity. So if any issues with inverses, review or any problems with inverses. I mean, it takes time to get used to it, but really it's not really that complicated. I think the right point of view is really helps if you just keep the variable straight. X input, y output, and then you just do the other way around. Y becomes the input and x the output, and then you realize it's the same thing. Pretty much, it's the same function. It's just the same relation rather between the two variables. It just happens to be reversed, either flip the which one is the dependent variable. Okay, so and then the pair of exponential functions that pair of function inverse that we didn't discuss. We talked about roots. Okay, so every root is the inverse of a power. Okay, there is also what else? The two at least the two trig functions have inverses. Okay, arcsine, arcsine, and then one we did not discuss is the exponential function. What's the inverse of the exponential function? What undoes the effect of the exponential function? No. Well, we'll get to that. I want to quickly review the exponential functions as they're being built. Unlike some of the functions that we have seen elsewhere, such as, say, polynomials, there's really no doubt about how the function is being computed. You just plug in the values and then you carry out operations that are very specific: addition, subtraction, multiplication, division. Okay, and then you take inverses. You have roots. All kinds of functions appear in that manner very easily. Trig functions are also have this geometric meaning. Remember, it is the x and y coordinates of the point on the unit circle. Okay, where's that discussion that we had? Well, some point ago. So anyway, there is some geometry behind it, and with exponential functions, there is really no explicit geometry behind it that we can use in order to define the function through, at least on the intuitive level. So that's it's true to an extent that we could do it this way. So exponentiation is just repeated multiplication. Okay, so as you can see, you just to take if x is a natural number, then all you have to do is just to multiply a by itself x times. Okay, so if x is 1, 2, 3, 4, and so on, that's the meaning of natural numbers. The exponentiation is simply the powers. Okay, so it's if we know how to multiply, then we can get exponential function, right? It's just you repeat the multiplication, but it's not what the difference is. It's not the power. Remember the difference between the powers. Say, what's the difference between 2 to the x and x squared? You see the difference? The variable is different. So even though you might compute in a similar way, but the variable is different. So in the latter case, you're given that real number x and you multiply by itself, the meaning of which will be like if x is given, what you're talking about the area of a square with side x. Okay, so it's clear how you do it by multiplication. It's clear what the geometric meaning is. With the exponential function, not so much, unless x is an integer. Okay, and that's just a start. You just put these points, what points that just talked about, when x is 1, 2, 3, 4. 1, 2, 3, 4. To the 0th power, it is 1. As you should know that if I take to the power of 1, that will be a. Okay, and then I take the next one, this will be a squared, and so on, a cubed. All of these can be computed by this direct computation, but the function has more than that. Okay, it has more than that because you look, I only have the blue points that I can compute, and it does not create a whole function. So the only way I have to find a way somehow to get all of these values in between to fill them in, and the answer is to first figure out the way for rational exponents. So say a 1/2. So I'm talking about this point right here. What's the meaning of a 1/2? Square root of 1/2. Square root of a. Okay. Okay. So I don't want to talk about. We just talked yesterday about the meaning of the square root. The meaning of the square root is the inverse of the square. Same applies to any other root, 1/3 cubic root of a. Okay, so all of fractions like that, all fractions with all reciprocals are understood as the inverses of the corresponding power. Okay. However, now what about 3/2? So now I have 1/2, 1/3, and so 1/4. All of these taken care of. What about 3/2, which is right here? 3/2. What's the meaning of 3/2? A 3/2.
Is it the square root of a times 3? Or to the
No, times to the third power, yes. To the third power, or which is the same thing, a cubed square root, it doesn't matter. Okay, so same thing. So we know powers of integers, we know roots. Combined together, those fractions, so those fractional, or also known as rational exponents, x could be rational, we can take care of it. Rational number, remember, it is just a fraction, so it's a p over q, some integer, and you can compute it as just taking qth root of a. That's where the denominator goes, and the numerator goes in the as a power, as exponent. Okay, so as long as the exponent is rational, we can compute it in this manner. So with the understanding of the repeated multiplication, so this is repeated multiplication, and that one is root, the inverse of the corresponding power. Okay, so that is, once again, can be done, but that's still not enough. Not every number is rational. You know that? Not every number can be represented as a fraction. So example of the rational numbers: pi, square root of 2, a bunch of them. So what do we do? What do we do? How do we define? Say 2 to pi. Okay, so I'm talking pi is here somewhere. Okay, so I need a point on the graph to know where it is. So what do we do? Now that's a challenging question, actually. How do we define 2 to the power of pi? What we have been talking about actually brings us to the point that we can actually say what this is. So once again, remember that this part is very helpful. We can handle rational exponents. How do we get from rational to irrational? So rational here, and irrational there. But there's no wall between them. In fact, they're spread out like this: rational, irrational. So how does that help? Yeah. So look for the starting point for numbers. What kind of numbers? For rational numbers around pi. Okay, so it's a starting point. That is the idea, the correct idea. But we have to make it more specific. So And then what? Can you suggest any numbers we should look at? Any rational numbers around pi?
3.
3, okay. More?
4.
No, how about 3.1?
Yeah.
3.14. 3.145. 3.14. No, wait a minute. Well, it is a 1 here.
5.
This is a
3.1415.
yeah.
And some for 2 6 or something.
Yeah. Well, you get the idea. So we take the decimals. The decimal, we take the more and more decimals of the representation of pi. Okay, so these are rational. These are all rational. And why do we choose it this way? What's the point of this? It's a sequence. And what's so special about the sequence?
Looks random.
No, it doesn't. Look at how I accumulate digits. And these digits are the digits of pi, right? So what's the point of the sequence? What's the question we always ask about sequences?
What's the limit?
What's its limit? Pi. Okay. Okay. So then the point being that we know 2 cubed, 2 3.1, 2.314, 2 3.141, 2 3.1415. All of these we understand because we know how to handle exponents with a rational argument. Okay, so we can compute all of these. Okay, so what's the last step then? We have created a new sequence, and same question, where does it converge? What's the limit? No. 2 to the pi, yes. Which was that was our concern. How to compute to the pi when pi is not a rational number. And that's the answer. The answer, you find a sequence converging to pi, and then of rational numbers, compute the power, the exponential function of those numbers, and then look at its limit. Okay, and then say this is 2 to the pi. The situation similar to this, what we looked at not too long ago. Well, that's a bad example. This is a good example. Bad example meaning a negative example. This is a positive example. So as you can see, we were in a better place. We approximated with the green sequence over there. We approximated 0, which is a good number as it is, but suppose that we have a number that is irrational, and then the only way to deal really with irrational numbers computationally is approximate them with rational numbers. That's the idea of decimals. We have as many decimals as necessary for our computations, but we also remember that there are infinitely many of them. So theoretically we can treat it in this fashion. So that number, imagine that at the left bottom corner, it's not 0, it's pi. Then you have a sequence of green numbers, and you can choose rational numbers converging to it. And then you compute the values of the function that we already can handle, producing the blue numbers. Okay, and then that creates the missing value. So if there was a hole in the graph of this function, now there is no hole anymore because we have filled it with this value. So one point at a time, eliminate holes. So if you do all rational numbers, and by the way, rational numbers are all everywhere, so they don't seem to have any gaps visible. So when you only plot rational functions, the graph of that function over there will look exactly like this. It will look like a complete curve, but there are invisible gaps there. Not gaps, rather. Gap is probably not a good word. The gap, I feel the word gap means some kind of a distance. But these are not distances. There are no distances. Every interval you take, there will be rational numbers both as well as a rational number there. But if you take one point at a time, there will be cuts, I would say. Okay, so for example, if I take a pi right here, then there will be a missing point on the graph, even though it is surrounded so densely by other points that it's invisible. So the graph looks like a curve, but actually a bunch of numbers are missing. But well, doing it this way, essentially we're saying is that let the graph be what it looks like. So with rational numbers, we build the graph, okay, and then we just say, well, whatever is missing, let's just pretend that it's not missing, and then we're also building a function simultaneously to be continuous, because what is this if not the definition of continuity? This part. Remember, x converges to, say, a. F of x converges to f of a. That's what we're saying here. X and converges to a. F of x and converges to f of a. That's continuity. Okay? And that is now by design we constructed a function that satisfies this property. So that is how over like a century, like 19th century probably, roughly, when they were worked out these details and how to deal with the gaps between rational numbers that we can deal with and then real numbers that we really want, because we don't want to have missing points. If we're moving through space, we want to have every single point taken care of. So that's how they do it. So they took what came from calculus and the notion of limits, and then applied it to pretty much building functions in such a way that the function is not only it's built and it is defined, but it's also a continuous function. So that certainly is a bonus, even though it is by design. Okay, so that's how we build the rational function. It will, exponential function will look like this. Gaps are all gone, so this is what I have now. What I have here is a function like this. There is a bunch of functions that we have actually built. 2 to the x, 3 to the x starts lower but then grows faster. On the other hand, if I pick, say, 1.5 to the x, it will grow slower, start higher and then grows slower. And then what happens to the negative values? Remember the word for this? The word is the base. So exponential function base a, and a could be 1/2, 2, 3, whatever, any number as long as it's larger than 0. So the base may vary and the function vary. So I hope the picture looks slightly familiar. Okay, so what about base? What if base is 1/2 negative? Say -1. Hold on a second. What did I? Yeah. No, hold on. That's I messed up. What I meant here is not 1/2. I meant 3/2. Yeah. So we go down slightly from 2 to 3/2, and so the growth is slower. It's like a bank account, and depending on what kind of interest rate you got, you get faster growth. Okay. So if I am reducing the base from 3 to 2 to 3/2 more, what if I reduce to 1? What does it turn into? If the base is 1, what's the function? Straight line, horizontal line, right? This is 1 to the x, which is simply 1, and then you go with the base that is less than 1. So base, say 1/2. What base 1/2 is, you multiply 1/2 by itself, what do you get? 1/4. Yeah, so what does the graph look like? Yeah, it will be decreasing, just like what we discussed, what we called exponential decay. So this is exponential decay, as opposed to the other one, exponential growth. So this is exponential growth. So depending on the power, you have one or the other. The function looks similar. Functions look similar as long as either is on one side or the other. And we will study them all together rather than just trying to do it one by one. So exponential growth, the population grows, and you have a particular birth rate per population, which is typically the way it happens. Or you have population decay. Happens similarly when there are more people dying than being born. Okay, and then you have a decay, which is exponential. So, say for example, you lose 10% of the population every year, or every decade, and that's what you get. So eventually, you're supposed to end up with 0. And the radioactive. So you know what radiocarbon dating is? Yeah. So can you explain a couple of words?
So it's how they date the age of rocks and fossils in the ground.
I wouldn't say, I'm not sure about rocks and fossils. I'd say like objects man-made mostly, because made of plants. So say for example a paint in a painting is made from a plant, and what happens is the plant, they know what that plant is, and it contains particular percentage of particular radioactive element. Okay, when it's alive. When it's cut, decay starts. And then if you compare how much you've got in the painting of that uranium or whatever, not uranium, but carbon, forgot the name, how much you've got of it in comparison to the actual plant, you know how much time has passed. And you know when the tree was cut to produce the paint. And that applies to materials, all kinds of it was remember that shroud of Turin. That's what they did. Also, there was, because if there is any kind of plant or animal elements immersed embedded in the material, then you can try that to do that. So all kinds of books where the paint is also to write or print it might have animal or plant base, and then you do radiocarbon dating, and that's the exponential decay function is being used. So, for example, typically like 5,000 years for the amount of that radioactive material to lose half of its amount. Like 5,000 that's half-life. That's what it's called. So if you know half-life, you know the element, you can test it. You can know how fast it is decaying. So then you have the graph. And then you just say, well, if we are right here, then, well, this might be 5,000 years. It means that when it was cut right here, it was say 5,000 years ago, and that's the date roughly. So it could still be younger, but it cannot be older. So that's the conflict. Usually they say this is 1,000 years old, and then you do computations only 500s. The tree was cut 500 years ago, so it cannot possibly be made before that. Well, there are certainly errors that I've heard of, but generally it's pretty well established technique. Okay, so that's why we study exponential functions. The inverse of the exponential function is, nobody remembers?
Is it a logarithm?
It is a logarithm, right? The logarithm, right? So 2 to the x inverse log base 2x. Okay, so let's put a y here as I have. So x is equal to log base 2 of y. So y is equal to the x. X is equal to log base 2 of y. So in other words, to what power? That's what I have on the right. X is the power to which I raise 2 to get y. So the explanation of what's on the right is on the left. That's how a lot of functions are created. They are not created through computations, but they are created by saying, well, let this function be the inverse of the function that we already know. So if you know the exponential function, you spend so much time to figuring it out, and then they create a new function by saying, well, let's create a function and name it. There is nothing mysterious about the logarithm. It is simply the inverse of the exponential function, and that is where it comes from, and there is no other meaning behind it. Same arcsine, arccosine, arctangent, they all have the same origin, the inverse. Square root, exactly the same. There is nothing to the square root other than that it is the inverse of the square. Okay, so that's how you produce more and more functions, and they certainly become more complex possibly. So logarithms are the inverses. Let me just for completeness sake, we have the graph of the logarithm, which will look just like those, like this. It looks like this. So this is, say, I put y here, x there. So this is x equal log base 2 of y. Okay, so that green one, dark green on the left, its inverse is here, log base 2 of y. Okay, so once again, everything comes in pairs. And then there is one special exponential function. Okay, so you can already guess. I wonder if you can guess. Well, compare those three functions that you see, base 3, 2, and 3/2. They are kind of similar, as they are all increasing, right? So ignore the orange one. Can you make one from the other?
What do you mean?
Well, there are one curve and then there is the other curve. They're kind of similar. Can you just, through some geometric manipulation to turn one into the other? Let me plot this clearer. Say this is 2 to the x, y is equal to 2 to the x, and the other one is 3 to the x. Okay, you see how, so both of them are increasing, they're passing through the same point, one over here, and I say there is a way to turn one into the other. Well, you remember, as a hint, remember the transformations of a plane that produce new functions. Remember any of those? Shift? Remember shifts? So for example, you can have a function shifted, a graph to be shifted vertically. What do you do to the function? Add 1, 2, 3, and it will go up and down. If you're negative 1, it goes down. Okay, so and then you can shift vertically, horizontally. What else do you remember about other transformations?
Well, if you mess with the coefficient, you could get to equal the same. But
Right, you could, but then I'm just wondering if you see how it happens geometrically. You could mess with the exponents, and you can transform one into the other. True. Which is what I'm driving at, as a matter of fact. And but geometrically, well, let me just demonstrate. You can stretch. Imagine stretching the xy plane horizontally, like this. Okay, so by what proportion you would have to figure it out separately, but it is at least conceivable that, like I said, you take a piece of rubber that is with one of the graphs drawn on it. Say the green one, 3 to the x, is drawn on it, and then you grab it like this and you stretch it. The graph becomes flatter, right? It's not going to be growing as fast anymore, and you conceivably can turn into the other graph. Okay. So it's very similar to what you've seen elsewhere, but it's really not a big trouble. I don't want to go into the algebra of this operation, but the point is that it can be done. All the functions, exponential functions, are very similar, and that is the reason why we should probably study only one exponential function to begin with, because they are all similar. So you can produce new functions. It's just like you start with x squared, right, and then through shifts and stretches, you can get any quadratic function. Okay, so if you understand x squared, a parabola, then you can shift it at any location, and you can flip it upside down, remember that one, and stretch vertically or horizontally. As a result, you can get any of this. That's why this is the real one, and the rest of them are kind of derived from it. Okay, so that makes life easier if you just find in any large group of functions, you find one that is a representative, so you don't have to worry about the rest of them. Okay, so similarly, we could think of a function that serves as a good representative of the function of all of these functions of exponential functions, and the answer is, the answer is which one. if you know the answer. It's kind of hard to pick which one would be natural choice for a natural choice for such an exponential function. So the exponents, the bases, run from say from 1 to infinity. So base a, right, is just larger. Let's say larger than 1, and they all look like this. So which one to pick? It's certainly not 1 because it's giving you a horizontal line. There is none. It appears there is nothing. There is no number that is especially important. But actually, there is an answer, and we pick the one that crosses the y-axis at 45 degrees. In other words, the slope is 1. Okay, so like this. And here, over here, this is 45 degrees. 45 degrees. Okay, so that's the one we pick. So what's the base? And the base is E. That is a special number that comes from this kind of analysis, that there is a special base. Another, by the way, another irrational number, E is also irrational, a transcendental, in fact, number. And there's where it comes from. It is kind of we choose it as the representative of all exponential functions. Because you start with this one and you can get all of these through this manipulation, through horizontal stretching. Okay, so even though, remember, we can actually be solving a problem that is entirely about something, say maybe the compounded interest on your bank account. So the interest is say, if you have 10%, you have 1.1 to the power of x. That is your exponential function. The 0.1 every year you multiply by 0.1. So that is your exponential function. And then we say, well, actually it is better still to do it through E. For one reason, every calculator has E in it, and but not necessarily the rest of them. And the logarithm, as you might remember, ex, y is equal to ex. The inverse is, remember that one? You can look, what? Natural log, ln y. That's what. ln stands for natural, yeah. And so natural exponential function, e to the x, natural logarithm is ln y. Okay, so in other words, log base e of y. So with that choice, we could concentrate on them, and that fact that it crosses at 45 degrees is going to be really helpful. But in that number e is also comes from a limit. Okay, so that might serve as the definition of the exponential function. It's if you think about it, there you probably could. I don't want to do it, but certainly worth mentioning that where this number e comes from, it might come from considering the compounded interest compounded continuously. Have you heard of it? So we usually either compound once a year, once a quarter, right? If you keep doing it better and better job, you want to compound it every month, every week, every day, and then you end up with a sequence. And the limit of that sequence is e. So roughly speaking, if you are, say your APR is 100%, so hypothetically, you are doubling your money every year, okay, if you are compounded once a year. If you compound it twice a year, you'll get a little bit more. Compound 4 times a year, you get yet more time. So more and more often you compound your interest in your bank, more money you get. But the interesting thing is that you're not ending up with an infinite amount. You're ending up with E. So if your APR is 100%, so you get at best, no matter how many times you compound, you get at most E dollars per dollar. So if you compound once you get $2. If you compound infinitely many times, you get E dollars, which is number is larger than 2, less than 3. Okay, so there's a limit to that, to how well you can do if you keep going to your bank and trying to get higher and higher, not high interest, but rather try to get them to compound your interest more and more often. And turns out the answer is limited by E. Okay. But this one is actually probably is more important, this thing, that it crosses at 45 degrees, the slope is 1. That is a lot of calculus will be relying on that. Okay, so there's still left quite a bit of stuff that we need to talk about as far as the continuity is concerned. And for one, let's look at the you might remember theorems about limits of sequences, and just at least 2 or 3, and they all have counterparts with limits of functions. So, for example, it is the comparison test. So let's say f of x is less than or equal to g of x. Okay, and then, so suppose their limits have the same inequality between them. Okay? There's a caveat here. I wonder if you remember from discussion about limits of sequences. So there are 2 functions or 2 sequences. They have an equality between them, and then we conclude that their limits also have that inequality between them, provided what should be the caveat? So we're speaking of limits as numbers, right? So you cannot speak of those 2 as limit. So you have to require that limit exists in the first place. Okay, so because then otherwise maybe it doesn't exist. Can you compare 2 things that don't exist in the first place? So then you don't want to make a conclusion that cannot possibly be true. If the 2 limits don't exist, they cannot possibly have any relation between them. Or even one of them doesn't exist, still that doesn't work. So provided both exist. Okay, if both of them exist, then we have an equality. So one function lying below the other function, then here somewhere at A, the limit will be of the first will be below the second. So this is F and this is G. Okay, so then this is, and these are the 2 limits. There is a little bit of, so that's the first part. The second part is what to do with infinities. Okay, so suppose we still have that inequality, but what if one of the limits is infinite? So suppose like this. Case 1, limit f of x is equal to, say, plus infinity. Can you draw any conclusion?
G of x would have to equal plus infinity.
That's right. So limit g of x is also equal to plus infinity. What if it's minus infinity? Then what?
G of x has to be equal or greater than negative infinity.
Which is, what does that mean exactly?
All round numbers.
even less than more. In fact, it's still possible that it could be negative infinity, it could be positive infinity, it could be any number. It could diverge either. So then we did not narrow down things at all. So it's still, everything is still possible. So the answer is no information, no new information that we can derive about G. Okay. Similarly, we could say that limit of G, say limit of G of x, if that one is equal to negative infinity. So we are the larger function goes to negative infinity. What does it mean? What does it mean for a smaller function? The larger function goes to negative infinity. What does it mean about the smaller?
The smaller function is negative.
Also has to go to negative infinity. But if the larger function goes to positive infinity, that doesn't mean anything. Nothing. Okay. So that's one. The theorem we can justify all of this with the sequences as before, because all the limits of functions are defined through limits of sequences. Okay. So one more theorem from before was the Squeeze theorem. So that's what I want to add. Also. Okay. So the Squeeze theorem. So that is when one function is squeezed by two. So this one was like one function is dominated by the other, and sometimes it means something, sometimes it doesn't mean anything. But when a function is dominated by two, just like with sequences, so say f of x less than or equal to h of x less than or equal to g of x. So once again, the sandwich situation. Okay, sandwich. Something is sandwiched between two, squeezed or held by two functions that have something behavior of which at a limit is known. So then in addition to this, then we can make conclusions about h. So suppose limit f of x is equal to limit of g of x, let's say equal to L. So these exist. Okay, then so not only both of them exist, but they are equal to each other. Once again, remember the sandwich is taken to wherever the bonds go. If they go to the same place, then whatever is inside the sandwich also goes to that place. So if you that's a crucial part of information. So if your one bond goes to your left pocket and the other bond goes to the right pocket, then you have no control. You have no idea where the rest of the sandwich went. But when they go to the same place, then you're good. And so you conclude then the limit of h also exists and equal to L. Okay, the standard example is once again as we did before. X sine x. I remember we plotted this one. So h of x is equal to x sine x. You can plot it to confirm that it does appear that the function is convergent. Has a limit at 0. It looks like this. Well, roughly speaking. Okay, and then you're supposed to squeeze it between the two. How? Well, usually you just start with sine x between -1 and 1, so some trigonometry helps. And then if sine between x and x, then x sine x, well, this one is a bit tricky, lies between what? Between what two functions? One will be this, and the other will be that. That's the squeeze. Do you see what those functions are?
Absolute value.
Absolute value on the right and negative absolute value on the left. Okay, and then these are really simple functions. We replace this complex function with unknown behavior with infinitely many oscillations. I'm sorry, I actually meant sine 1 of x. I'm sorry about that. Sine x is not really an interesting function at all. I mean, it has a limit, so that's not interesting. Sine 1/x does that oscillation that we see on the right, and so it's really hard to, even numerically might be hard to do, because any kind of computation might get stuck or just stop. And so, but analytically, you replace this complex function with two really simple functions. Look at them, absolute value of x, negative absolute value of x, and they have limits, right? So limit, let me just write the limit. So this one goes to 0, and this goes to 0 as x goes to 0 from left or right or simultaneously. And then we conclude by the Squeeze theorem that limit x sine 1/x, x goes to 0 is also equal to 0. Okay? Okay, so what else we have here? Some functions are even nastier than that. Well, so there are some global properties of continuous functions, something that did not come up during the study of the sequences. So sequences are entirely about limits, but some of the functions, some of the information about the function is more interesting of continuous functions. And primarily, these are very predictable in the sense that once you have this intuition of functions, of continuous functions, having graphs like curves with no interruptions, no gaps, no cuts either. So, for example, this might look like looks very nice, but really there is a little cut there. Okay, so that's not continuous because if there's a missing point there, that's not continuous. But once you understand that there are no cuts, so if you like grab it by two, you grab it here, you grab it there, okay? You take it here with 2 fingers and you start pulling, and it does not pull. That one on the right will be pulled apart. So that's the difference between continuous and not continuous. If you can, from that, you can make some conclusions, which we're going to be doing next time, okay? So I'll assign a homework tonight.